Thank you, everybody, for hopping on this call. Really appreciate it. Taylor, Carolyn, and I were chatting right before we opened up the gates, let you in, and we realized this is our 1-year anniversary as a meetup, which is really exciting. Thank you, everybody, for keeping us going. We've had like a pretty consistent, growing group of people who show up, which is just we really appreciate it. Can't do this without you. I think our conversations have, started great and have gotten more mature and more exciting. I've met a lot of you during our time at CDS, so I appreciate it. Yeah, and with that, I think we're going to continue going. Year 2, here we go. And we have some amazing speakers today. We have Jay and Yoav. They're each going to speak on their respective topics. Just so those who are new, welcome. And we have a Q&A feature that you're more than welcome to. They can't see or hear you, but I know that you guys have a Q&A button. You can click and type a question. They can see those questions. And each talk will be about 20 minutes long. And after that, we'll have about 10 minutes of Q&A with the speakers themselves, which please ask all the questions you have. We'll help facilitate that, but please feel free to ask any questions you have. But without further ado, I'd love to introduce our first speaker. Here's Jay. By the way, Jay and I are in the same location. Isn't that fun? Jay is a doctor of data science at Axis, which is the ticketing company spelled AXS, and he's very excited to show you what his presentation is. So I'm going to turn the mic over to Jay, but give him a warm welcome.
Thank you, Adam. Thanks so much for giving me the stage. Let me share my screen. Can you see my screen? Can anyone see my screen?
Yep, we can see your screen.
Okay, great. So first of all, I'm very glad to start the year 2 with this meetup with you together. And I hope everyone is safe and well and managed to find something interesting and meaningful to do during quarantine, such as joining this meetup. Today, I would like to discuss something very common in machine learning, which is categorical attributes. To start, just a couple categories about myself. I am currently the director of data science at Axis, which is a ticketing company. And I started my so far, I spent my career almost entirely in entertainment industry. I started at Legendary, which is a movie production company. Before Applied Analytics division that I was in were acquired by Warner Media and spent 2 years there before joining Axis. My background is mostly analytics and engineering, and of course, machine learning. And the work I've done experience in social media data mining, the modeling of customers and markets, and some digital marketing. The categories I mentioned are examples of categorical attributes. They are very common in their science, especially when you're working with customer data. The categorical attributes are, variables that contain label values instead of numeric values. And for example, for customer, we might know their interests, their skills, their locations, their educations. They're all represented by different levels of string in the database. Most of the time, they hide or mask a lot of interesting information in the data set, and sometimes it could be likely the important attributes in a model. But before we can import them, before we can use them in the model, we need to first encode them first. There are 2 common encoding methods in machine learning. First is ordinal encoding. You just assign one number to each level. So in this case, if we have ABC level for a type for a category, then we might just assign number 1 to 3. But this is only applicable in certain scenarios. For example, if there's orders, if the levels have some ordinal relationships, or they're applicable to specific algorithms such as tree-based models. So the other methods are, the other method is one-hot encoding, which is one that I use pretty often. So the idea here is just to assign a vector of 0 and 1 to each level. So for example, if we have 3 types in total, then we assign a vector of dimension 3. And for the first one, the ID one, then we have type A. So therefore, the column of type A will be assigned the value 1 with the rest as 0. And the same goes on for the others. This is pretty easy to implement and understand, but there are several drawbacks. One of them is the high dimensions might result in very sparse data representation. Therefore, it might require very substantial computation resources. And also the different levels are treated independent. As you can see, they're flock-node to each other. So the information between them are always ignored. And finally, in terms of implementation, the new levels are either ignored or there might be some complexity in the engineering pipeline. So is there anything we can do to improve this? So let's look at deep learning. So deep learning or deep neural network has become the standard when dealing with unstructured data, such as video and audio. But can it help with the structured data? In our case, the categorical variables that we look at? The answer is yes. And idea is kind of sort of combining the previous 2 encoding techniques. So in this case, we just assign a fixed size numerical vector to each level. So this technique is called entity embedding. So the concept is kind of similar to word2vec, if you've heard of it, or collaborative filtering, although the actual implementations is different. But the idea here is that for each level, instead of represented just by one number, it represented by a vector. So we have a much richer representation. For example, in this case, if we have a vector of dimension like say 3, and to represent a first type, we might have 0.3 in the first dimension, 0.5 in the second, and 0.2 in the third. So the question is, how do we get the number? How can we find the representation of the vector for each categories or for each level? So the idea to learn entity embedding is to train a neural network. So the idea here is that we build a neural network with a target variable as an output and categorical attributes as an input layer. Notice that the primary purpose of this is to learn and extract the feature representation rather than minimize the loss or have the maximum predictive power. Although we can do that with the correct configuration and structure. But in this case, what we are most interested at is the embedding for each attribute. So the dimensions and structure must be determined beforehand. And embedding is actually learned during the standard supervised training process. And once we have finished up the training, the learned embedding could be extracted or used as input for other models and applications, such as input for linear regression or for regression model, or as the initial weight for the other models. So let's visualize it. So this is a standard feed-forward neural network with 2 hidden layers. So this is just a structure that I picked, which is somewhat a sensible default. But you can definitely add more layers or tweak the structure of it. And the output layer here is the target variables that we want to learn the representation from. And we have 2 hidden layers here. One of them are embedding layers, and trace back to the input layer. In this case, input are the categorical attributes. When I do research about this, I actually find that there are different ways to interpret the input layer. But I find the most intuitive way to understand it is for each neuron, just think of it, conceptualize it as one level from the categorical attributes. So if there are, like say dimension n, then there are like number of n neurons here. And each of the input layer is connected to the first hidden dense layer or the labeled embedding layer. and which each of them is associated with the weight. And the weight here is optimized through the standardized training of the neural network, is optimized through the backpropagation. So the weight for each neuron that connects to the embedding layer is exactly the embedding that we are looking for that level. And different categorical attributes and even the numerical attributes can be concatenated in the input layer together, so that we can learn the representation of embedding for all the categorical variables altogether at once. One thing that I forgot to mention here is the dimensions of their embeddings. So this is something that's actually is a hybrid parameter that we can tune, that we can decide beforehand or through experimentation. Empirically, it could be the number, the half of the number of different levels, or we can set the maximum cap for those with a very high dimensions, so that we can have a reasonable number of embeddings. Of course, the actual number depends on how complex the relationship you want to embed. So let's look at some of the benefits and drawbacks of this entity embedding. So some of the benefits are we have a reduced number of dimensions, and memory usage compared to one-hot encoding, and it's robust to the number of levels because it doesn't affect the engineering pipeline. All it happens is in the neural network training stage. And what's best is that it can reveal the intrinsic property of categorical attributes, and we can learn embeddings that could visualize to see what's the relationship. And the ones that are close to each other, they would be naturally grouped together. Of course, there are some drawbacks. For example, they are harder to explain compared to ordinary encoding or the one-hot encoding. And there might need some additional efforts to implement to build up this neural network structure. And finding the optimal representation might be tricky, say, to determine the different number of dimensions. But in general, it has been shown that the performance of using entity embedding has greatly helped the traditional machine learning methods, such as Great Boosting Machine or Random Forest. And it can be used by data science in almost any industry, because I believe the structured data are, the data science encounter quite often in their daily work. And of course, the last point is, of course, it's unknown like which technique will work best in the particular application. So the best way to do is just to try out different different encoding techniques and see which one works best in your scenario. So talking about implementation of this, if you have experience with some deep learning frameworks such as Keras, it's not particularly difficult to implement it, to code it up from scratch. But the process of pre-processing the data, getting the embeddings or transforming the data might get repetitive or sometimes cumbersome. So I found there are like some open packages online that can help simplify this process. So with just a couple lines of code, you can accomplish this process using this open source package. For example, on the left, if we look at the Embedder package, what it does is reading the data and determining from the data what are the categorical variables are, and determine the dimension of embedding. In this case, it's either the number of categories or using maximum dimensions. And it prepare the work for the deep learning framework for the the required formats, and then just initiate and fit this embedder. So all this can be accomplished in just several lines of code. Of course, you could also build it from scratch using Keras, which will be more flexible. Now I would like to show two examples. One example has come from the Kaggle context a couple years ago. So the author looks at the historical sales data for stores in German, and each store is located in a specific German state. And the task is to predict the sale for each store. And the team is actually able to achieve, I think, third place using the entity embedding compared to the somewhat complicated approach for the first and second place team. And the visualizing embedding of these states actually surprisingly clusters similar to the state's geographical location, even though this information was not available in the model. Another example I would like to give is actually from my work. So it's an artist genre mapping. So what I did is to learn mapping of the genre for an artist through modeling against their popularity and demand. And then I visualized the learned mapping in 2 dimensions. I find it's really interesting that similar genres are grouped together. For example, the K-pop and pop genre, they are close to each other. The rock and hard rock, they are close to each other. And the hip hop, electronic, and reggae, which at least in my opinion, they're similar and they are grouped together. One thing I would like to, I find particularly interesting is that during the processing stage, I forgot to kind of like standardize the case for this Christian genre, resulting in one in capital, first one in capital case, in uppercase, and the other in lowercase. But it turns out they grouped together. So I found this pretty interesting, and this result could be, a very very helpful input for later stage, such as learning and applying to some machine learning model compared to just using plain one-hot encoding. All right, that's all I want to share. Thanks so much for sharing time with me, and I hope it's helpful. Now I'm open to questions.
Awesome. Thank you so much, Jay. I think if you can open up that Q&A chat, I don't know if you can see it. There are 3 questions already lined up for you to maybe kind of walk through with the audience.
Yep. Okay. So I saw Joseph ask, would 0.03 be a probability? My intuitive answer is that it's not a probability, although I think this probably comes from what I showed, like an example values here and 0.3, and they add up together, add up to 1. But in this case, I think the representation or the embedded values, they will be optimized and learned throughout the training and or the optimization of the neural network. So I don't think it could be, I don't think it is a probability in this case. All right, another question is, how does this compare to a method like clustering the categorical features based off the outcome data? And then one-hot encoding the cluster. I think this is a good good question. In my experience, I think this, at least from the example I show, I find that the learned result are pretty intuitive. And if you want to do, like clustering the categorical features, I think the key question here is how to determine the distance between, the different levels. And I think that's pretty, that's very vital in determining, how successful the clustering is. And in this case, it's kind of like essentially it's like through building out this neural network, it helps you to find the intrinsic relationship between the different levels of the categorical features. So yeah, I think in some sense it's kind of similar to finding the cluster of the categorical features throughout this neural network.
Awesome. Thank you for the answer.
The next question is, when training a neural network for creating and embedding, what is used as target value? This is the question. So the target value in this case is the one that you want the embedding to approach to approximate from. So for example, in the store cells examples, it uses the store cells as the target variable. And in the case that in my work, I use the popularity of the artist as the target variables. So I would say whatever the one that you would want to find, you want embedding to find representation from, and use that target variable so that they can get close to it. So Katie asked, can you share a couple of examples of what this approach should or shouldn't be used for when it comes to customer analytic use case? Yeah, as I mentioned, there are some drawbacks and benefits for each of the encoding techniques. So I would say just keep those in mind when you use this one or versus the others, and try them out. For example, if you want to use as input for a predictive model, and try to do different encoding and see which one brings you to the best result. And I think the different encoding methods would be different for different application scenarios.
So Jay, I actually had a question for you.
Yep.
You made an interesting point about when you're building and embedding net, that you can have a target outcome obviously tied to the input so that you're building and embedding, but you're not necessarily focused on getting the lowest loss possible for the outcome variable. Are there particular loss functions you find valuable in training a neural network such that the embedding gets stronger because we're not actually looking for lowest loss or something like that?
Yeah, good point. So for examples I tried, or so like for regression task, I just use a mean square error, and for classification task, I just use a cost entropy loss. In most of the cases, they are sensible default to use, and I don't think I have tried the other loss function because as I mentioned, the primary purpose of this neural network is not to minimize the loss, rather to learn the embedding. Of course, I think if the predictive power of the neural network is strong, then the embedding would definitely be better than ones that less has less predictive power. But I think the main point is that we don't want to spend too much time just kind of fine tune the model, because the main purpose here is to just get embedding.
Awesome, thank you. That's very helpful.
Yeah, and I saw there's a last question here from Yang. Can the target be binary, like for classification problem? And the answer is definitely yes. But the thing to notice that is just that you need to use a different loss function, and in this case, to use a cost entropy loss for classification.
Awesome. I think if anyone has any dying last questions, please speak now or forever hold your peace. And if not, Jay, how can people reach you if they have any future questions? Do you have an email or something like that we can share after the meeting?
Oh, yes, definitely. I can share my email address, or you can find me through my LinkedIn.
Perfect. Well, awesome. Thank you so much, Jay, for the presentation on embeddings. I think that's really interesting, especially since one-hot encoding and label encoding are such common uses for categorical variables. Seeing a third option that is more sophisticated and provides some explanatory power is really cool. It's a very, very exciting way to see it. And that was cool to see how Axis is even using that in production, which is great. And with that, I'd love to transition over from Jay, which thank you so much, to our second speaker, Yoav. Yoav is also in a tropical vacation with all three of us. Yoav is the founder of Model Zoo, and I think his presentation today will be speaking towards that. Model Zoo, just for those who don't know, is an ML infrastructure company. And I'm sure Yoav knows a lot more than me, so I'd like to turn the floor over to Yoav for his presentation.
All right, great. So thank you, Adam, for that introduction. I am sharing my screen now. Let's see here. There we go. All right. So, Adam, can you confirm that you see my screen?
Yes, I can see your screen.
Okay, excellent. All right. So today I'm going to be talking about deploying machine learning models for real-time inference on Amazon Web Services. So I've been working a lot in this area for my startup. So I thought it'd be interesting to talk about kind of a little bit about how I built this infrastructure. So this presentation will actually be a little bit more flavored towards the infrastructure and systems versus data science, but it will also have some components of machine learning. All right, so this is kind of the layout of what I'm going to be talking about today. So first, we're going to just give a brief overview of like what is deployment in machine learning, and then we're going to set up kind of a toy problem. We're going to talk about some solutions, just kind of from a high-level point of view, just drawing some boxes on the screen, and then I'm going to do a little demo of how you would deploy a TensorFlow model. Cool. All right, so let's dive in. So this is a little bit about me. My expertise is mainly in machine learning, software engineering, and I've also done some like DevOps and infrastructure engineering. So I've done a little bit of both, both on the data science side, developing models, and then also on the systems side, actually getting these models in production and like monitoring these in production. So I went to college at UCLA, spent some time at Google working on applied NLP use cases, and then also spent some time at Determined AI, which is a startup that's focused on deep learning training infrastructure. And now I'm working on this company called Model Zoo, which is in the machine learning infrastructure space, and with the goal of helping people deploy models easier. So I've done some work with some financial companies, biotech, advertising, self-driving. This is through Determined AI, where we had clients in these different industries. All right, so first let's start at the kind of machine learning development lifecycle. So you might have seen different versions of this graph at different points. Basically, when you start a machine learning project, you're probably going to be on the left over here. You need to kind of understand what is it you're actually trying to accomplish here. Then you start getting into your data, and then you develop your model, and so on and so forth. And then this final step is this deployment and operationalization step. And this is the step that you get to when you say, okay, I have a model. Maybe it's a pickle file from scikit-learn, or maybe it's a saved model file from TensorFlow. Now you want to figure out how do you actually use this in production. And this is a really important step. We're actually finding in industry that more and more companies are starting to face this step kind of as the big data and machine learning world becomes more and more sophisticated. People are figuring out how to train models, and now they finally want to use these models. So there are a few different types of machine learning deployments. I kind of categorize them into these three areas. So the first on the very left here is this area of offline scoring. So in this case, basically you have a large data set and you want to use the model to make predictions on that large data set. But maybe you're doing that offline, right? So you're not interacting directly with customers. Maybe you're a pharmaceutical company and you want to process a large data set of drugs. So you can kind of kick off a job at the end of the day, go to bed. It takes a few hours, and you come back and it's done, and you can kind of continue your analysis. This was similar to something we did at Google, which, we had an algorithm that ran, or a model that ran over the entire web. So it took like 10 hours to run. So it was run on a daily basis. And typically these offline scoring jobs are kind of automated and run, daily, hourly on some sort of cadence. The next category is this online scoring category. So this is if the model is needed to make real-time predictions. And these are on-demand predictions where you don't know what the input is going to be ahead of time, right? So a great example of this is you have a consumer app that identifies a product based on a picture that you took. So you want to take a picture of a wine bottle or something and have it return the label or the price. And if you're building an infrastructure for an app like this, then you're not going to know, the user's picture ahead of time. So it's important that you can set up an infrastructure such that, a model can take a picture from a user, calculate its predictions, and return it on the order of like seconds or something like that. Now, the final type is what I call on device. And this is also an online prediction method, but typically in these cases, latency is a very, very strict requirement. And this model needs to be really, really fast. And that typically leads to the requirement that the model actually needs to be on a device instead of, in the cloud or on a server somewhere. So self-driving cars is the perfect example of this. If you have a car speeding down the road at 80 miles per hour and the camera sees a pedestrian, it needs to be able to make a decision in, split second, whether it's going to stop or turn or whatever. So these kinds of scenarios, you're designing for much different requirements because, you might not have access to the internet on your device, or you might not have as much memory as you would on a server. So it's important to know actually kind of as early as possible in this process, which category roughly you're going to end up at, because that's actually has implications for how large your model can be and how you want to serve it and so on. Another way to think about this, these differences is by asking the question, how fast does the model have to run, right? So on the very left here, it doesn't really, the model can run in like a few hours. It's typically in these use cases, it's not too essential that, you need to get a prediction for a single data point very quickly. It's typically more about, how do we, get predictions for like millions of these points in a few hours. Now, as you go down these use cases, like in the middle here, if you have a model that is being used in an app or for an app, your user is probably going to want to, get a response within the order of seconds. Maybe it's not a, life-critical decision, but it's something that needs to be, reasonably fast to make the app usable. And then on the very right here, of course, you need decisions in nanoseconds. It's critical for safety and just for the use case. Cool. So we're going to focus on this middle type of model deployment. And there's a lot of really fascinating things to talk about for the other categories too, but we just will not have the time today. You could spend an hour on each of these. So let's set up an interesting problem here. So what we're going to do is we're going to design a model for a wine detection app. So if you like wine, there's this app called Vivino. It's pretty fun. You basically take a picture of the wine bottle and then it tells you how expensive it is and what store it's from, that kind of stuff. So let's assume we have a model. And now we're going to need to figure out how do we get this model to production, right? So some data scientist, or maybe you or an ML engineer have already figured out here, we collected our training data, we've trained this model, we have the model in this Jupyter notebook. Now we have to figure out how do we actually make this app work around it. So whenever you're designing a system, it's usually a good idea to start with the requirements. So let's talk about some of the typical requirements that you see with online machine learning serving systems. So the first is latency, right? How fast does a single prediction need to be? In our, for our problem here, this means, how long does a user have to wait to get a result? For this wine app, a second is probably fine. It's not, no one's dying to you know, figure out the price of their wine. But again, if it gets over a few seconds, maybe it'll be a little annoying to use the app. So we want to keep it reasonable. Throughput, this is how many requests can we serve at once? So how many users can use the app at once? This starts to become a little more important if you have, you know, a system that's with a lot of users. Do you expect there to be like 50,000 users of this wine app, or is it just kind of like a prototype that you're just starting out with and just sharing it with a few friends? You're going to want to know that ahead of time to figure out, you know, how you're going to design this system. Cost. How much is it going to cost to maintain these resources? So if any of you deal with like cloud infrastructure at your company, you'll know, you know, how large these bills can get to. And it's really important to, it's always a good, you know, design factor to figure out, you know, what's the right cost? How do I optimize the cost for my, my app here? Because this is going to translate to how much the app costs to your users, potentially. And then also technical complexity. How hard is it to build and maintain, right? We don't want to go down a rabbit hole and spend like years building this like, you know, extremely custom system. We want it to be able, you know, we have a limited bandwidth of engineers. Maybe we don't want to hire too many people. So we want to, you know, have it be reasonable to build it, maybe use open source components where we can. All right, so we've set up our requirements. So now let's get into some solutions. Cool. So basically, I'll go over a few different solutions with a focus on AWS. And I have this little chart here that kind of compares each of these solutions to our different requirements here. Designing systems is all about trade-offs. So some of the solutions are going to have, you know, be better for certain requirements. Some of them are going to be worse. So let's start with kind of the easiest possible or the most naive kind of solution we can come up with. And actually, you know, if you Google today, like deploy TensorFlow model, you're probably going to come across a tutorial that does something like this. So in this kind of box, we have our AWS infrastructure. This is kind of like the cloud. And in this box, we have a web server that is serving the model via HTTP requests. So I'm being kind of hand wavy right now. You know, there is some code associated with this. Maybe it's containerized. But for our purposes, you know, at a high level, it's a single process that accepts HTTP connections, that HTTP requests that have the data for the model, and then it returns the prediction of the model. And that goes directly to each of our users, which are either on phone or maybe they're on web browser. And you can set this up by using Amazon EC2, which is their technology for just spinning up a VM, just getting like a virtual computer. This is a really nice solution because it's really simple comparatively. It's pretty cheap to get a EC2 machine. It's going to run you like, you know, like a few dollars a month maybe. The latency is pretty good because there's, you know, only kind of one layer here to go directly from the client to the server. We start to run into problems with throughput, right? You only have one server here, so you're actually, potentially, it's gonna get really slow. Let's say it might take, you know, half a second to make, for this server to calculate a prediction for a single data point. That means the server can only serve 2 requests per second. And, you know, if you have a bunch of people labeling wines right before dinner, like 100, 200 people, a bunch of them are going to get errors. So we're not going to be able to support some of the throughput requirements that we want in certain scenarios. So next we go to this thing called load balancing. So this is kind of typically how you deal with a lot of requests in not just machine learning systems, but in a lot of different systems. Machine learning has this type of machine learning inference has this nice property that it's horizontally scalable. So you can actually create a bunch of copies of these servers. Each one of them has a copy of the model, and each one of them has its own HTTP server that's running. And you put a load balancer in front of it, and the load balancer's job is just to take these HTTP requests from the clients and basically distribute them across the servers. So there's a bunch of different ways, strategies for load balancing. Sometimes it does like round robin. Sometimes it just like picks random servers, but basically we can assume that it can distribute the load, and you can now handle more requests, and you can just continue adding servers for as many as you want. And again, this can all be handled within Amazon EC2. So they have load balancers. They also have VMs that you can use. So, so yeah, so now our throughput's good. But now we're starting to trade off cost a little bit. And it's starting to get a little more complicated. So what do I mean by cost? Well, if you want to serve at a, the peak of your traffic, let's say your usage graph looks like this, and at 1:15, for whatever reason, every day, 800 people use the app, whereas your steady usage is like 200. So now you're going to want enough replicas to serve traffic at your peak usage, but for the rest of the day, you're not going to be utilizing that usage. So it's just going to be really expensive. You're going to pay 8 times the cost of what you would pay for solution 1, and really, you're not going to really need it. You're only going to need it at like a certain time in the day, potentially. So that brings us to solution 3. So this is where we start bringing in the magic word Kubernetes. You might have heard this word if you work with infrastructure a lot. There's also an AWS product called Elastic Container Service, which does a similar thing. But basically, what Kubernetes does is it's an open source resource manager that helps us abstract away some of these common types of tasks. So for example, there are packages on Kubernetes you can use that will actually auto scale your replicas up and down based on how many requests are coming in per second in your load balancer. So it will be able to detect, at 1 p.m. there's a lot of requests coming in. Okay, let's scale up our replicas. And then a little bit after, there's not that many requests coming in. Okay, let's scale down to save costs. So this is great. It's the most flexible solution, but now it's getting kind of complicated. If you're building a prototype, for instance, this is probably a little heavyweight for you to do. It might take you like a week, or sorry, months, and it might kind of really delay your project from getting like user feedback or something. So this is really only a solution you'll want to go to if you're going to have to build kind of a heavyweight system that handles a lot of load. So now there's a 4th solution on AWS, which is also kind of interesting. This is a relatively new movement called serverless. So serverless is on AWS. It's a technology called Lambda, and basically what this does is it allows you to abstract away servers. So you don't have to worry about auto scaling, replicas, concurrency, all that stuff. You just give AWS basically some code, and AWS will then take that code and execute it for you. So if that code is just like a machine learning model, then it can also help you with machine learning inference. So this is kind of what the diagram looks like. So there's also this thing called API Gateway in AWS, in addition to Lambda, and it's a much simpler architecture, much simpler box than this, but it can still handle auto scaling. It's just that AWS kind of handles that behind the scenes for you. So it'll horizontally scale for you, so you don't have to worry about throughput problems. It's not complicated to maintain, which is really nice. You can spin up a server really quickly, or a Lambda very quickly. The cost can get a little more expensive if you're doing it at scale. So if you have over like 2 million requests per month, it gets a little pricey. And also there's some latency issues sometimes when the first time you are hitting your Lambda, you're making an HTTP request. After a long time of inactivity, you can run into some latency problems. And this is just the tip of the iceberg, right? So this is kind of a picture of the Model U architecture. So you can see there's a lot of different kind of boxes here, and we don't have time today to talk about all of them. And actually, just deploying your model and getting it to serve HTTP requests at scale is only one problem in a set of a lot of subproblems in production ML. So that, you know, you're going to want monitoring, logging, feature store, model registry, and so on and so forth. As your kind of ML organization, ML infrastructure grows in sophistication, there's going to be a lot more things you kind of want to add. And a lot of different profiles that interact with it too, right? So you're going to have your data scientists that deal with your models. You're going to have your clients, maybe your product teams that write the, you know, front-end code that interact with these models. And you're also going to have your DevOps team that's maybe maintaining the underlying infrastructure and responsible for the AWS accounts and that kind of stuff. So it gets complicated. Cool. All right. So with that, I'm going to get into a demo. So for this demo, what I'm going to be doing is demoing kind of a little bit of the software that I've been working on, the Model Zoo platform. We're going to use it to train and deploy a TensorFlow model. All right. So I'm going to be sharing my screen right now to a terminal. Here we go. All right, so we are, can everyone see it?
Yep.
Great. So we are in an IPython terminal right now, which is my terminal of choice. So the first things I'm going to do is import NumPy and TensorFlow. I'm going to copy paste in some code right now that basically trains a TensorFlow model. So it's kind of like a lot of code, but basically what it's doing is it's using TensorFlow to initialize a neural network right here with an Atom optimizer and some loss, and then it's training it on the fashion MNIST data set. So this is a fairly small model, and I'm training it for a very small amount of time, just for demonstration. And I'm only training it for 5 epochs, and I'm training it on a data set that can kind of fit in memory on my laptop. And after a few kind of log messages down here, you see it's been trained for 5 epochs, and now we have this model. Cool. So I can do model.summary, and you can see kind of this is what the model looks like in TensorFlow, a single dense layer, about 100,000 parameters. So the next thing I'll do is I'll call like model evaluate just to evaluate it on our test set, just to see what kind of accuracy it gets. So this is still kind of on my local machine. You can see, okay, cool, we got the test accuracy of 87%. That's not that great for MNIST, but for demonstration purposes, it'll have to do. So now I want to go and deploy this model. So a cool thing about the way I've been building Model Zoo is you can do this straight from Notebook or from your IPython terminal. So the first thing I'm going to do is I'm going to import our client library, and then I'm going to type in the function that is used to deploy the model with our deploy function, and I'm just passing it the model object directly. So now under the scenes, what's happening is the model is being serialized, and then it's being uploaded. And then my software is kind of creating all of this AWS infrastructure under the hood that I was just talking about. And now it's kind of waiting for that model to start up. A Docker container is being created, the Docker container is being downloaded on my AWS infrastructure, and very soon the model will be ready for production. So while that's getting ready, I'm going to switch screens back over to Chrome here to show you kind of what the UI looks like. So this is the UI on the front end. You can see that this is the model I've just created. It's still kind of loading right now. So I'll just go to an example model that I kind of preloaded before. And you can see the UI gets kind of like, you get some like nice information here. So I have some documentation associated with the model. I can edit it. This is kind of a fun tab. This is, in this particular case, this is an object detection model. So I can kind of click different pictures and get some results. I can even have like a webcam here. So let's see if my webcam works. Wasn't able to detect. Okay, there we go. So I got a person and even a little bit of my chair. Great. And you know, you got a bunch of bells and whistles and stuff, logs, metrics, that kind of stuff. Cool. All righty. So getting back to my terminal here, it looks like our model's ready. And there's also a client library that is able to do predictions. Yeah. Cool. So what did I just do here? I have a test label. I was able to use the model to predict on like a test image. What that did is it actually made an HTTP request, got back scores, and then generated a model prediction, which is the same as the ground truth. Cool. So we got our model predicting. We got our model deployed to an HTTP endpoint, ready to serve productions by any client libraries, apps, and stuff in a few minutes. Cool. So that's the demo. And just as kind of a final slide, I'll transition here. Here we go. Cool. So this is kind of some of my contact information down here. If you work with model deployments or models in production at all, I'd love to talk about anything, even if you just want to kind of like learn a bit more about how you should build your own system in production, or just want to kind of bounce around ideas. I'm also running a referral program for August. So if you know anyone that would be interesting for me to work with and that could be valuable, that it would be valuable for me to work with them, I'm offering some nice referral bonuses, actually like a percentage of basically my first year revenue from that person that you referred me to. August only. And then of course, feel free to add me on LinkedIn, Twitter, send me an email. I'm always open to talk about machine learning and machine learning in production. All right.
Awesome. Thank you so much, Yoav. Again, feel free to ask him any questions in the Q&A area or chat. I had a quick question, Yoav, which is just, you made the comment that obviously I'm a data scientist by training, not much experience in the infrastructure world. You talked about if I had some mock-up or some prototype, what would be the best of the options you talked about today for me to kind of get something going, just to see if it worked, just to see if it made sense for our business? Like, what would that look like?
Yeah. I have been playing with Lambda a lot recently, and I actually think it's really nice, a really nice option for if you're using a prototype, if you just have a prototype. It's nice because it's fairly low complexity. So I don't think if you don't have a lot of experience with AWS infrastructure, it's not as difficult as some of the other options are to like ramp up. And it also has a pretty nice cost model. So you don't have to, you can just deploy as many as you want, and you're only paying per request. So you don't have to worry about, accidentally spinning up too many services and overpaying. You can just, you're only really going to pay if as much as the model is being used. And one more thing I can mention as well is I have an open source package I've actually released that I've open sourced kind of one of the components of Model Zoo that makes like this specific scenario easy to do on your own infrastructure if you're using scikit-learn models. So that's another thing happy to talk about if anyone's interested.
Cool. Awesome. Thank you.
Yeah. So Joseph asks, have you played with Kubeflow? Yes. Kubeflow is great. I've played with it a lot. So for those in the audience that don't know about Kubeflow, Kubeflow is basically a package that you deploy on top of Kubernetes. So you can deploy a Kubernetes cluster on any cloud infrastructure like AWS, Azure, GCP. And then Kubeflow will abstract away some different pieces of infrastructure that you need to do a bunch of different things in the machine learning development lifecycle. So it actually helps you train models. It helps you deploy them. It helps you monitor them. I think it has some like data labeling stuff too and explainability stuff. So Kubeflow, if you're going with an open source option and you want to kind of deploy, you want to give your IT people, DevOps people, or if you do DevOps, want to kind of play around with something, Kubeflow is a great option. There's another few open source options that I would I can also kind of recommend to you. The reason that or the fact that Kubeflow exists and a bunch of great open source options exist was kind of a good reason for me to kind of not rebuild Kubeflow. I think there's a lot of good open source options out there, and with Models, I'm really aiming for it to be super easy as a platform. So you can just kind of like pip install anywhere and just deploy to it and not have to worry about underlying infrastructure. But thanks for that question, Joseph.
So I don't know, this Henry P has thrown a wrench into this because he says he's raising his hand. I don't know if that means you have a question, Henry. Yeah, maybe I'll click allow to talk and see if Henry will say something. This is
Henry. Let's talk.
I don't know. I think Henry put his hand down.
He put his hand down. I bet it was like an accident, like accidentally pressed on it or something. Okay, that's okay, Henry. We can talk later.
Oh yeah, Yoav, could you put back up how we can get connected with you?
Oh yeah, you got it.
Love more questions.
Yep. Feel free to add me on any channel you'd like. Cool. All right. Well, thank you so much to everyone. I think it's 7, so we're coming up on the hour. Hope everyone has a good night. Thank you, Adam, and the Retina AI team for letting me talk, and I'll catch you guys later.
Yeah, thank you so much, Yoav. Thank you so much, Jay and Yoav, and everyone who came to talk at our annual, first year done CES talk. This was great. As usual, Carolyn will send out a video recording of this along with their slides. So if you have any questions later, you can definitely reach out to them. Again, I appreciate everybody coming out for the talk on a Wednesday night, and I hope to see you guys all here again next month. Cheers and have a good night.